Now let's just move on further towards the theorem next, which is nothing but in a parallelogram opposite angles are equal. So we just have to prove that the opposite angles are equal in a parallelogram. So let us suppose if I'm just drawing a parallelogram over here, let us suppose if I'm just taking a parallelogram as this. This is nothing but my parallelogram I'm taking, and I'm calling this as nothing but A, B, C, D, such that I'm taking this as nothing but a diagonal over here. Now I just have to prove that the opposite angles are actually equal to each other. So let us suppose if I'm just taking a given condition that A, B, C, D is a parallelogram. It is a parallelogram. And furthermore, we just have to prove that angle A is equal to angle C and angle B is nothing but is equal to the angle D. This is the thing that we have to prove over here. So furthermore, we can say that we just start the proof of this one by just taking the only one thing over here. Since we know that in a parallelogram, AB is nothing but parallel to DC and CB is nothing but parallel to AD. So since ABCD is a parallelogram, it is nothing but a parallelogram. So we know that it implies that AB is parallel to DC and BC is parallel to AD. We already know about this particular concept. Now, if these are actually parallel to each other, so it implies that, let us suppose if I'm starting with since AB is parallel to DC, where AC is a transversal, so what can we say about the two angles? Since if AB is parallel to DC, let us suppose if I'm just taking this as nothing but angle 1, I'm taking this one as nothing but angle 2, I'm taking this one as the angle 3, I'm taking this one as nothing but the angle 4. So what can we say about the different angles over here? If AB and DC are parallel to each other, so we can say that angle 4 is nothing but is equal to the angle 1. Why so? Because they are forming a pair of alternate interior angles, and alternate interior angles are always equal to each other if we have the two parallels and a transversal. Let us suppose if I'm calling it as 1. Furthermore, I'm just talking about the second case in which we know that since BC is parallel to AD, where AC again is a transversal, again we are taking, so it implies that it is a transversal. It implies that the angle 2 will be equal to the angle 3. Why? So again they are forming a pair of alternate interior angles. Let us suppose if I'm calling it as nothing but 2. Now, since you can see over here, we have the two angles. So let us suppose if I am just writing it over here, that from equation number 1 and 2, what we are getting, let us suppose if I am writing them as angle 1 is equal to angle 4 we are getting, and angle 2 is equal to angle 3 we are getting. So let us suppose if I am adding equation number 3 and 4. Let us suppose if I'm taking it as 3, I'm taking it as 4. I'm adding these two equations. So this is angle 1 plus angle 2, which is equal to angle 4 plus angle 3. So angle 1 plus angle 2 is nothing but the whole angle A, and angle 3 plus angle 4 is nothing but the whole angle C. You can see over here that angle 1 plus angle 2 is forming a whole angle 3 plus angle 4 is actually forming a whole angle C. So hence at the end what we are getting, that angle A is nothing but is equal to the angle C, that is nothing but the opposite angles are actually equal to each other. So since in the same manner, if I'll just take a diagonal BD rather than AC, if I'll take BD, then I can definitely prove that this angle should be is equal to this angle. So let us suppose if I'm just taking a similarly, if BD is a diagonal, in ABCD parallelogram, it implies angle B is nothing but is equal to the angle D. And this is exactly what we have to prove over here, that in a parallelogram ABCD, the opposite angles are actually equal to each other. So this is nothing but the proof of this theorem.